What if the universe itself is hiding a secret so profound that it could rewrite everything we think we know about existence? Picture this: an invisible force, silent and unseen, is stretching the fabric of space faster and faster, pushing galaxies apart in a cosmic tug of war that defies the laws of physics as we know it. This force is dark energy, and it holds the key to some of the greatest mysteries of our universe. From the accelerating expansion of the cosmos to the ultimate fate of everything we see, dark energy is the enigmatic puzzle piece that scientists are still struggling to fit into the grand picture of reality. In this video, we're diving deep into the 25 mysteries of the cosmic dark energy era, exploring how this mysterious force shapes the universe and challenges our understanding of space, time, and existence itself. Stay with us, because by the end of this journey, you'll uncover mind-bending truths about the cosmos that will leave you questioning everything you thought you knew. Are you ready to explore the unknown? Let's begin. Now, let's take a closer look at one of the most groundbreaking discoveries in modern cosmology: the accelerating expansion of the universe. For decades, scientists believed that the universe was expanding, but they assumed this expansion was slowing down over time due to the pull of gravity. After all, gravity is the force that holds galaxies together and keeps planets in orbit. But in the late 1990s, something extraordinary happened. Two independent teams of astronomers studying distant supernovae made a startling observation. Instead of slowing down, the universe's expansion was speeding up. This discovery was so unexpected that it sent shockwaves through the scientific community. What could possibly be causing this acceleration? The answer, or at least the leading theory, points to dark energy. This mysterious force seems to be acting as a kind of anti-gravity, pushing galaxies apart at an ever-increasing rate. But here's the twist: dark energy doesn't behave like anything we've encountered before. It doesn't clump together like matter, and it doesn't interact with light or any other form of electromagnetic radiation. In fact, the only way we know it exists is through its effects on the large-scale structure of the universe. This discovery fundamentally challenges our understanding of physics. For one, it raises questions about the nature of gravity itself. Einstein's theory of general relativity, which has been the cornerstone of modern physics, doesn't fully account for this accelerating expansion. Some scientists have even proposed that we might need a new theory of gravity altogether. Others suggest that dark energy could be a property of space itself, a kind of energy inherent to the vacuum of the cosmos. The implications are profound. If dark energy continues to drive the universe's expansion, it could determine the ultimate fate of everything we see. But for now, it remains one of the greatest mysteries in science, a puzzle that challenges our deepest assumptions about the cosmos. And as we move forward, we'll explore how this discovery has reshaped our understanding of the universe and opened up new frontiers in the search for answers. Next, we'll dive into the role of supernovae in uncovering this cosmic mystery, and how these exploding stars became the key to unlocking the secrets of dark energy. Now, let's turn our attention to the cosmic detectives that helped uncover this mystery. Type 1, a supernova. These stellar explosions are not just spectacular events in the night sky. They are also incredibly precise tools for measuring vast distances across the universe. Here's how they work. Type 1, a supernova occur in binary star systems, where a white dwarf star pulls material from its companion until it reaches a critical mass and explodes. Because these explosions always reach roughly the same peak brightness, astronomers can use them as standard candles to calculate distances. By comparing how bright a supernova appears from Earth to its known intrinsic brightness, scientists can determine how far away it is. In the late 1990s, two teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, used this method to study distant supernovae. What they found was astonishing. The supernovae were fainter than expected, meaning they were farther away than predicted. This could only mean one thing: the universe wasn't just expanding, it was accelerating. The team's findings were so consistent and compelling that they earned the two lead scientists, Saul Perlmutter and Adam Rees, along with Brian Schmidt, the Nobel Prize in Physics in 2011. But why are Type 1, a supernova, so special? Unlike other types of supernova, which can vary widely in brightness, Type 1 explosions are remarkably consistent. This uniformity makes them ideal for measuring cosmic distances with incredible precision. Without them, we might never have discovered the accelerating expansion of the universe. The discovery also highlights the ingenuity of astronomers. By carefully observing these distant explosions and analyzing their light, they were able to piece together a story that reshaped our understanding of the cosmos. It's a reminder that sometimes the answers to the universe's biggest questions come from the most unexpected places, like the death throes of a star billions of light years away. As we continue our journey through the mysteries of dark energy, we'll explore how this discovery has led to even more questions about the nature of the universe. Next, we'll delve into the enigmatic properties of dark energy itself and why it continues to baffle scientists to this day. Now, let's shift our focus to the heart of the mystery, the nature of dark energy itself. What exactly is this mysterious force that's driving the universe to expand faster and faster? Unlike gravity, which pulls objects together, dark energy seems to do the opposite. It pushes space itself apart. This strange behavior makes it one of the most puzzling phenomena in modern cosmology. Dark energy is invisible, doesn't interact with light, and doesn't clump together like matter. In fact, it appears to be evenly spread throughout the universe, filling the vast emptiness of space. This uniformity is one of the reasons it's so hard to detect directly. Unlike dark matter, which we can infer from its gravitational effects on galaxies, dark energy's influence is more subtle and pervasive. It's not pulling things together, it's stretching the fabric of the cosmos itself. One of the most intriguing properties of dark energy is its density. Unlike matter, which becomes less dense as the universe expands, dark energy's density seems to stay constant or even increase over time. This means that as the universe grows larger, dark energy's influence becomes stronger, accelerating the expansion even further. It's as if the universe has a built-in engine that keeps pushing it to expand faster and faster. But what makes dark energy truly baffling is how little we know about it. We can measure its effects, but its origin and true nature remain a mystery. Is it a property of space itself, as Einstein's cosmological constant suggests? Or is it something entirely different, like a dynamic field that changes over time? These questions are at the forefront of modern physics, and answering them could revolutionize our understanding of the universe. As we continue to explore the mysteries of dark energy, we'll dive deeper into some of the leading theories that attempt to explain its behavior. Next, we'll examine Einstein's cosmological constant and how it might hold the key to understanding this enigmatic force. Now, let's turn our attention to one of the most fascinating ideas in the quest to understand dark energy, Einstein's cosmological constant. This concept, first introduced by Albert Einstein over a century ago, has taken on new life in modern cosmology as a potential explanation for the mysterious force driving the universe's accelerated expansion. But what exactly is the cosmological constant, and why does it matter in the context of dark energy? When Einstein developed his theory of general relativity, he introduced the cosmological constant as a mathematical term to balance the equations and describe a static universe, one that wasn't expanding or contracting. At the time, this was the prevailing view of the cosmos. However, when Edwin Hubble discovered that the universe was actually expanding, Einstein famously called the cosmological constant his greatest blunder and abandoned the idea. But as it turns out, the story didn't end there. In the late 1990s, when astronomers observed that the universe's expansion was accelerating, the cosmological constant made a dramatic comeback. Scientists realized that this term could represent a form of energy inherent to space itself, a kind of background energy that permeates the cosmos and drives its expansion. This energy, now associated with dark energy, could explain why the universe isn't just expanding but doing so at an ever-increasing rate. One of the strengths of the cosmological constant as an explanation for dark energy is its simplicity. It suggests that dark energy is a property of space itself, a constant energy density that doesn't dilute as the universe expands. This idea aligns well with observations of the universe's large-scale structure and the cosmic microwave background. It also fits neatly into the framework of general relativity, making it an elegant solution to a complex problem. However, the cosmological constant isn't without its challenges. One major limitation is the so-called cosmological constant problem. According to quantum field theory, the vacuum energy of empty space should be vastly larger than the observed value of dark energy. This discrepancy is one of the biggest unsolved puzzles in physics, raising questions about whether the cosmological constant is the full story, or if there's more to dark energy than we currently understand. Another issue is that the cosmological constant assumes dark energy's density remains constant over time. While this matches current observations, it doesn't account for the possibility that dark energy's properties might change. Some theories propose that dark energy could be dynamic, evolving as the universe ages. If true, this would mean the cosmological constant is only part of the picture, and a more nuanced explanation is needed. Despite these limitations, the cosmological constant remains one of the leading candidates for explaining dark energy. It provides a solid foundation for understanding the universe's accelerated expansion, even as it raises profound questions about the nature of space, time, and energy. As we continue to explore the mysteries of dark energy, the cosmological constant serves as both a guide and a challenge, pushing us to rethink our understanding of the cosmos. With this in mind, let's move forward to explore another intriguing possibility: the fate of the universe and how dark energy might shape its ultimate destiny. Now, let's shift our gaze to the future, a future shaped by the enigmatic force of dark energy. The fate of the universe is one of the most profound questions in cosmology, and dark energy plays a starring role in determining how it all might end. Depending on how dark energy behaves over time, the cosmos could face one of several dramatic destinies: the Big Freeze, the Big Rip, or even the Big Crunch. Each scenario paints a vastly different picture of the universe's ultimate fate, and understanding them gives us a glimpse into the cosmic forces at play. First, let's consider the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to drive the universe's accelerated expansion, causing galaxies to drift farther and farther apart. Over trillions of years, stars will exhaust their fuel, galaxies will fade, and the universe will grow colder and darker. Eventually, all that remains will be a vast, empty expanse with temperatures approaching absolute zero. It's a chilling thought, a universe where all activity ceases and time itself seems to stretch into eternity. But what if dark energy becomes even more dominant? This brings us to the Big Rip, a far more violent end. In this scenario, dark energy's influence grows stronger over time, eventually overpowering all other forces in the universe. Galaxies, stars, and even atoms would be torn apart as the fabric of space itself stretches to its breaking point. The universe would end not with a whimper, but with a catastrophic rupture, leaving behind a fragmented, lifeless void. The Big Rip is a stark reminder of just how powerful and potentially destructive dark energy could be. On the other hand, there's the Big Crunch, a scenario where dark energy's influence weakens, allowing gravity to take the reins once more. In this case, the universe's expansion would slow, stop, and eventually reverse. Galaxies would collide, stars would explode, and the cosmos would collapse back into an infinitely dense point, a mirror image of the Big Bang. Some theories even suggest that this collapse could trigger a new Big Bang, creating a cyclical universe that endlessly expands and contracts. The Big Crunch offers a glimmer of hope, suggesting that the end of one universe could be the beginning of another. Each of these scenarios hinges on the behavior of dark energy, a force we still don't fully understand. Will it remain constant, as the cosmological constant suggests? Or could it evolve, becoming stronger or weaker over time? The answers to these questions will determine not just the fate of the universe, but also our understanding of the fundamental laws that govern it. As we ponder these possibilities, it's worth remembering that the universe's fate is still an open question, one that challenges us to keep exploring, keep questioning, and keep pushing the boundaries of our knowledge. And with that, let's turn our attention to another cosmic puzzle, the Hubble tension, and why it's causing such a stir in the world of cosmology. Now, let's dive into a cosmic conundrum that has left scientists scratching their heads, the Hubble tension. This mystery revolves around a puzzling discrepancy in how fast the universe is expanding. On one hand, we have measurements based on the cosmic microwave background, the faint afterglow of the Big Bang, which suggest a specific rate of expansion. On the other hand, observations of nearby galaxies and supernovae point to a slightly faster rate. This inconsistency, known as the Hubble tension, has become one of the most pressing challenges in modern cosmology. So, why does this matter? The expansion rate of the universe, often referred to as the Hubble constant, is a cornerstone of our understanding of the cosmos. It helps us determine the age of the universe, the distances between galaxies, and even the behavior of dark energy. But when two reliable methods give us different answers, it raises questions about whether we're missing something fundamental in our models. One possibility is that our understanding of dark energy is incomplete. If dark energy behaves differently than we currently assume, perhaps changing over time or interacting with other forces in unexpected ways, it could explain the discrepancy. Alternatively, there might be unknown components in the universe, like new types of particles or fields, that are influencing the expansion rate in ways we haven't yet detected. Some scientists have even speculated that our current theories of gravity might need revising to account for this tension. The Hubble tension isn't just a technical disagreement, it's a window into the deeper mysteries of the universe. Resolving it could lead to groundbreaking discoveries, reshaping our understanding of everything from the nature of dark energy to the very fabric of space-time. As researchers continue to refine their measurements and explore new theories, the Hubble tension remains a tantalizing puzzle, reminding us that the cosmos still holds many secrets waiting to be uncovered. With this mystery in mind, let's turn our attention to another key piece of the cosmic puzzle, the cosmic microwave background, and how it provides vital clues about dark energy and the early universe. Now, let's journey back in time to the very dawn of the universe, where the cosmic microwave background, or CMB, holds the key to unlocking some of the deepest mysteries of dark energy. This faint glow, often called the afterglow of the Big Bang, is the oldest light in the cosmos, dating back to when the universe was just 380,000 years old. It's like a cosmic snapshot capturing the universe in its infancy, and it's packed with clues about how dark energy has shaped the cosmos ever since. The CMB is more than just a relic of the past, it's a treasure trove of information. By studying its subtle variations in temperature and density, scientists can map out the early universe's structure and composition. These tiny fluctuations, no larger than 1 part in 100,000, reveal how matter and energy were distributed back then. But here's where dark energy comes into play. The patterns in the CMB tell us how the universe has expanded over billions of years, and they provide critical evidence for the existence of dark energy. Without it, the universe's expansion wouldn't match what we observe today. One of the most fascinating aspects of the CMB is how it helps us measure the universe's geometry. Thanks to dark energy, the universe appears to be flat on large scales, a conclusion drawn from the precise measurements of the CMB. This flatness is a direct consequence of dark energy's influence, which counteracts the gravitational pull of matter and drives the universe's accelerated expansion. The CMB also allows us to estimate the amount of dark energy in the cosmos, giving us a clearer picture of how it dominates the universe's energy budget. But the CMB doesn't just confirm dark energy's existence, it also raises new questions. For instance, the CMB's measurements of the universe's expansion rate sometimes clash with those from other methods, like observations of nearby galaxies. This discrepancy, known as the Hubble tension, hints that there might be more to dark energy than we currently understand. Could dark energy be evolving over time? Or are there other forces at work that we haven't yet discovered? The CMB keeps us asking these questions, pushing the boundaries of our knowledge. As we continue to study the cosmic microwave background, we're not just looking back in time, we're also peering into the future. The CMB helps us predict how dark energy will shape the universe's destiny, whether it will lead to a big freeze, a big rip, or something entirely unexpected. It's a reminder that the universe's story is still being written, and dark energy is one of its most enigmatic authors. With the CMB shedding light on the early universe, let's now explore how dark energy influences the large-scale structure of the cosmos, shaping the vast web of galaxies and galaxy clusters that stretch across the universe. Now, shifting our gaze to the grand tapestry of the cosmos, let's explore how dark energy shapes the large-scale structure of the universe. Imagine the universe as a vast, intricate web, with galaxies and galaxy clusters strung together like beads on invisible threads. This cosmic web didn't form by chance. It's the result of a delicate interplay between gravity and dark energy, two forces that have been shaping the universe since its earliest moments. Gravity, as we know, pulls matter together. In the early universe, tiny fluctuations in density caused by quantum fluctuations grew over time, thanks to gravity's relentless pull. These regions of higher density became the seeds for galaxies and galaxy clusters. But here's where dark energy steps in. As the universe expanded, dark energy began to dominate, acting as a kind of cosmic repulsion that counteracts gravity's pull. This tug-of-war between gravity and dark energy has shaped the distribution of matter on the largest scales. One of the most striking features of the universe's large-scale structure is the cosmic web itself. This web is made up of filaments of galaxies, vast voids of empty space, and dense clusters where galaxies are packed tightly together. Dark energy plays a crucial role in this structure. By driving the accelerated expansion of the universe, it stretches the cosmic web, causing the voids to grow larger and the filaments to become more diffuse over time. This means that the universe's structure is not static. It's constantly evolving, with dark energy as the unseen architect. But how do we study this vast cosmic web? Astronomers use powerful telescopes and surveys to map the distribution of galaxies across the universe. Projects like the Sloan Digital Sky Survey have revealed the intricate patterns of the cosmic web in stunning detail. By measuring the distances between galaxies and their clustering patterns, scientists can infer the influence of dark energy. These observations show that dark energy not only affects the universe's expansion, but also shapes the way galaxies are distributed, leaving its imprint on the cosmic web. Interestingly, the cosmic web also provides clues about the nature of dark energy itself. For example, the rate at which galaxy clusters form and grow can tell us how dark energy behaves over time. If dark energy's strength changes, it could alter the growth of these structures, leaving subtle signatures in the cosmic web. This makes the large-scale structure of the universe a powerful tool for probing the mysteries of dark energy. As we continue to map the cosmic web, we're not just uncovering the universe's structure, we're also piecing together the story of how dark energy has shaped it. From the tiniest fluctuations in the early universe to the vast voids and filaments we see today, dark energy's influence is everywhere. And as we delve deeper into this cosmic puzzle, we're reminded that the universe is far more dynamic and mysterious than we ever imagined. With a cosmic web revealing the fingerprints of dark energy, let's now turn our attention to another intriguing mystery, the vacuum energy paradox, and why the predicted value of vacuum energy differs so drastically from the effects we observe in the cosmos. Now let's dive into one of the most perplexing puzzles in modern cosmology, the vacuum energy paradox. At its core, this mystery revolves around the concept of vacuum energy, a form of energy that exists even in the emptiest regions of space. According to quantum mechanics, empty space isn't truly empty. It's teeming with fleeting particles and fields that pop in and out of existence. These quantum fluctuations give rise to vacuum energy, which, in theory, should contribute to the universe's expansion. But here's where things get strange. When scientists calculate the predicted value of vacuum energy based on quantum theory, the result is staggeringly large, so large, in fact, that it should have caused the universe to expand at an unimaginable rate, tearing apart galaxies, stars, and even atoms long before they could form. Yet, when we observe the effects of dark energy in the cosmos, its influence is far, far weaker than what quantum theory predicts. This enormous discrepancy between prediction and observation is what we call the vacuum energy paradox. So, why does this paradox exist? One possibility is that our understanding of quantum mechanics and gravity is incomplete. Quantum theory works incredibly well at describing the behavior of particles on the smallest scales, while general relativity explains the large-scale structure of the universe. But when it comes to combining these two frameworks to explain vacuum energy, the math breaks down. This suggests that there's a deeper, more fundamental theory of physics waiting to be discovered, one that can bridge the gap between the quantum world and the cosmos. Another intriguing idea is that vacuum energy might be cancelled out by some unknown mechanism. For example, certain theories propose that additional fields or symmetries in nature could counteract the effects of vacuum energy, leaving behind the much smaller amount we observe as dark energy. While this remains speculative, it highlights the creative ways scientists are trying to solve this puzzle. The vacuum energy paradox isn't just a theoretical curiosity, it has profound implications for our understanding of the universe. If we can unravel this mystery, it could lead to groundbreaking insights into the nature of space, time, and energy itself. It might even help us answer one of the biggest questions in cosmology: why is the universe the way it is? For now, the paradox stands as a reminder of how much we still have to learn about the cosmos. As we ponder the enigma of vacuum energy, let's shift our focus to another fascinating idea: quintessence, a dynamic field that some scientists believe could offer an alternative explanation for dark energy. Could this be the key to unlocking the secrets of the universe's expansion? Let's explore this possibility next. Now, let's turn our attention to a captivating idea that could reshape our understanding of dark energy: quintessence. Unlike the static nature of the cosmological constant, quintessence proposes that dark energy might be a dynamic field, one that changes over time and space. This concept takes its name from the ancient Greek term for fifth element, a substance believed to fill the heavens beyond the classical elements of earth, water, air, and fire. In modern cosmology, quintessence represents a new kind of energy field that permeates the universe, influencing its expansion in ways that are still being explored. So, how does quintessence differ from the cosmological constant? While the cosmological constant suggests that dark energy is a fixed property of space itself, quintessence introduces the idea that dark energy could vary. Imagine it as a kind of cosmic fluid, one that can thin out or become denser depending on the conditions of the universe. This flexibility allows quintessence to potentially explain why the universe's expansion rate has changed over time, something the cosmological constant struggles to account for. For instance, in the early universe, quintessence might have been more concentrated, driving rapid expansion, while today it could be more diffuse, resulting in the slower acceleration we observe. One of the most intriguing aspects of quintessence is its ability to interact with other forms of matter and energy. Unlike the cosmological constant, which remains passive, quintessence could exchange energy with the universe's contents, subtly altering the cosmic landscape. This interaction opens up new possibilities for understanding how dark energy influences the formation of galaxies, the distribution of cosmic voids, and even the fate of the universe itself. Could quintessence be the key to solving the vacuum energy paradox? Some scientists think so, as it offers a way to reconcile the observed effects of dark energy with the predictions of quantum theory. However, quintessence is not without its challenges. For one, its existence has yet to be confirmed by direct evidence. While it provides a compelling theoretical framework, scientists are still searching for observational clues that could prove its reality. Additionally, the nature of the quintessence field, its strength, behavior, and interactions remains largely speculative. This uncertainty makes it both an exciting and frustrating area of research, as it pushes the boundaries of our current understanding. Despite these challenges, quintessence represents a bold step forward in our quest to unravel the mysteries of dark energy. By proposing a dynamic alternative to the cosmological constant, it invites us to rethink the very fabric of the cosmos. Could this elusive field hold the answers to some of the universe's deepest questions? As we continue to explore this possibility, let's shift our gaze to another speculative yet fascinating idea: phantom energy, a form of dark energy that could lead to a dramatic and catastrophic end for the universe. What does this mean for the future of the cosmos? Let's find out next. Now, let's venture into a concept that takes the mystery of dark energy to an even more dramatic level: phantom energy. This speculative form of dark energy is not just a force driving the universe's expansion, it's a potential harbinger of its ultimate destruction. Unlike the more familiar ideas of dark energy, phantom energy suggests a scenario so extreme that it could tear the fabric of the cosmos apart in what scientists call the Big Rip. So, what exactly is phantom energy? Imagine dark energy as a force that grows stronger over time, rather than remaining constant or weakening. Phantom energy takes this idea to the extreme, proposing that its density increases as the universe expands. This means that, unlike the cosmological constant or even quintessence, phantom energy doesn't just push galaxies apart, it accelerates the expansion at an ever-increasing rate. Over time, this relentless force could become so powerful that it overcomes even the strongest bonds in the universe, from galaxies and stars to atoms themselves. The Big Rip scenario is the most dramatic outcome of phantom energy. In this vision of the future, the universe's expansion would accelerate to such an extent that everything, galaxies, planets, and even the fabric of space-time would be torn apart. Picture this: first, galaxies would be ripped away from one another, then stars within those galaxies would be pulled apart, and finally, even atoms and subatomic particles would be shredded. It's a cosmic apocalypse unlike anything we've ever imagined, and it all hinges on the behavior of this mysterious phantom energy. But why would phantom energy behave this way? The answer lies in its equation of state, a mathematical description of how its pressure relates to its energy density. For phantom energy, this value is less than -1, meaning its pressure is not just negative but increasingly so. This unusual property is what sets it apart from other forms of dark energy and makes the Big Rip a possibility. While it's still a speculative idea, the implications are profound, forcing us to reconsider not just the fate of the universe but also the nature of the forces that govern it. Of course, phantom energy is not without its challenges. For one, there's no direct evidence to support its existence, and its extreme behavior raises questions about the fundamental laws of physics. Could such a force truly exist, or is it a theoretical curiosity that pushes the boundaries of our understanding? Scientists are still exploring these questions, using observations of the universe's expansion and the distribution of galaxies to test the limits of this idea. Despite its speculative nature, phantom energy offers a fascinating glimpse into the potential extremes of cosmic evolution. It challenges us to think beyond the familiar and consider possibilities that are as awe-inspiring as they are unsettling. As we continue to explore the mysteries of dark energy, phantom energy reminds us that the universe is full of surprises, some of which could reshape our understanding of reality itself. With this dramatic possibility in mind, let's turn our attention to another frontier in the study of dark energy, the role of quantum gravity. How might the strange rules of the quantum world intersect with the vast forces shaping the cosmos? The answers could unlock even deeper secrets of the universe. Now, shifting our gaze to the microscopic realm, we encounter one of the most profound challenges in modern physics: the role of quantum gravity in understanding dark energy. While dark energy operates on cosmic scales, quantum gravity deals with the tiniest particles and the fabric of space-time itself. Bridging these two worlds is no small feat, but it could hold the key to unraveling some of the universe's deepest mysteries. Quantum gravity seeks to reconcile the two great pillars of modern physics: quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the force of gravity and the structure of the cosmos. These two theories have been incredibly successful in their respective domains, but they clash when applied together. For instance, general relativity describes gravity as the curvature of space-time, while quantum mechanics treats particles as discrete packets of energy. Combining these ideas into a single framework has proven to be one of the most elusive goals in science. So, how does this relate to dark energy? One possibility is that quantum gravity could provide a new perspective on the nature of dark energy itself. Some theories suggest that dark energy might arise from quantum fluctuations in the vacuum of space. These tiny, random fluctuations are a hallmark of quantum mechanics, and if they occur on a cosmic scale, they could contribute to the energy driving the universe's expansion. This idea ties dark energy directly to the quantum realm, offering a potential explanation for its mysterious properties. However, the challenges are immense. Quantum gravity theories, such as string theory and loop quantum gravity, are still in their infancy and lack experimental confirmation. These theories propose radically different views of space-time, suggesting it might be made up of tiny loops, strings, or even discrete building blocks. While these ideas are fascinating, they also complicate our understanding of dark energy. For example, if space-time has a granular structure at the quantum level, how does this affect the smooth, continuous expansion driven by dark energy? These questions remain unanswered, highlighting the complexity of unifying quantum mechanics and general relativity. Another intriguing possibility is that quantum gravity could reveal new forces or particles that interact with dark energy. Some researchers speculate that hidden dimensions or exotic particles predicted by quantum gravity theories might influence the behavior of dark energy in ways we don't yet understand. These ideas push the boundaries of our imagination, suggesting that the universe might be far stranger than we've ever imagined. Despite the challenges, the pursuit of quantum gravity offers a tantalizing opportunity to deepen our understanding of dark energy and the cosmos. By exploring the intersection of the very small and the very large, scientists hope to uncover a unified theory that explains everything from the behavior of particles to the fate of the universe. It's a monumental task, but one that could revolutionize our understanding of reality. As we ponder the mysteries of quantum gravity, let's turn our attention to another fascinating idea: the multiverse. Could dark energy be a consequence of our universe being just one of many in a vast cosmic landscape? The answers might be even more extraordinary than we've imagined. Now, let's venture into one of the most mind-bending ideas in modern cosmology, the multiverse. Could dark energy be a clue that our universe is just one of countless others in a vast cosmic tapestry? This concept, while controversial, offers a fascinating perspective on the nature of dark energy and the universe itself. The multiverse theory suggests that our universe might be one of many, each with its own unique set of physical laws and constants. In some of these universes, dark energy might behave differently, stronger, weaker, or even non-existent. But in our universe, dark energy appears to have just the right value to allow galaxies, stars, and ultimately life to form. This raises an intriguing question. Is dark energy a random feature of our universe, or is it a necessary ingredient for a cosmos capable of supporting life? One way to think about this is through the lens of the Anthropic principle. This idea suggests that the properties of our universe, including the value of dark energy, might be fine-tuned to allow life to exist. If there are countless universes with different values of dark energy, it's possible that only those with the right conditions like ours can support life. In this view, dark energy isn't just a cosmic mystery, it's a signpost pointing to the existence of a multiverse. But how could dark energy be connected to the multiverse? Some theories propose that dark energy arises from the interaction between our universe and others. For example, in certain models of string theory, our universe could be a brane floating in a higher dimensional space, with dark energy resulting from the gravitational pull of neighboring branes. These interactions might subtly influence the expansion of our universe, giving rise to the effects we attribute to dark energy. Another possibility is that dark energy is a remnant of the process that created our universe. If our universe emerged from a larger multiverse, the energy left over from that event could manifest as dark energy. This idea ties dark energy not just to the present state of the cosmos, but to its very origins, suggesting that the multiverse and dark energy might be deeply intertwined. Of course, the multiverse remains a highly speculative idea, with no direct evidence to confirm its existence. Critics argue that it's untestable and therefore falls outside the realm of science. Yet, for many researchers, the multiverse offers a compelling framework to explain why our universe has the properties it does, including the mysterious presence of dark energy. As we explore these ideas, it's worth remembering that the multiverse isn't just a scientific concept, it's a philosophical one as well. It challenges us to rethink our place in the cosmos and consider the possibility that our universe is just one small part of a much grander reality. Whether or not the multiverse exists, the questions it raises about dark energy and the nature of existence are profound. With this in mind, let's turn our attention to another intriguing concept, the Anthropic principle. How does this idea help us make sense of dark energy, and what does it tell us about the universe we live in? The answers might be closer than we think. Now, let's take a closer look at the Anthropic principle and how it might help us understand the role of dark energy in our universe. The Anthropic principle is a fascinating idea that suggests the properties of our universe, including the strength of dark energy, might be finely tuned to allow life to exist. In other words, if the universe were even slightly different, if dark energy were stronger or weaker, life as we know it might not have been possible. To put it simply, the Anthropic principle asks, why does our universe have the specific conditions it does? One possible answer is that these conditions are necessary for life to emerge. For example, if dark energy were much stronger, the universe would have expanded too quickly for galaxies and stars to form. On the other hand, if dark energy were much weaker, the universe might have collapsed back on itself long before life could develop. In this view, the value of dark energy isn't random, it's just right for a universe that can support life. But how does this connect to the broader picture? Some scientists argue that the anthropic principle might point to the existence of a multiverse. If there are countless universes, each with different physical laws and constants, it's possible that only those with the right conditions like ours can support life. In this scenario, dark energy isn't just a cosmic coincidence. It's a necessary feature of a universe capable of hosting life. Critics of the anthropic principle often argue that it's more of a philosophical idea than a scientific one. After all, it doesn't explain why the universe is fine-tuned. It simply observes that it is. However, for many researchers, the anthropic principle provides a useful framework for thinking about the unique properties of our universe, including the mysterious presence of dark energy. As we consider these ideas, it's worth reflecting on what they mean for our understanding of the cosmos. The anthropic principle challenges us to think about the universe not just as a collection of physical laws, but as a place where life can and does exist. Whether or not this principle holds the key to understanding dark energy, it certainly raises profound questions about the nature of our universe and our place within it. With this in mind, let's shift our focus to another critical tool in the study of dark energy, the Dark Energy Survey. How are scientists using this ambitious project to map the cosmos and uncover the secrets of dark energy? The answers might just reshape our understanding of the universe. Now, let's turn our attention to one of the most ambitious efforts to unravel the mysteries of dark energy, the Dark Energy Survey. This groundbreaking project, launched in 2013, represents a massive collaboration of scientists from around the world, all working together to map the cosmos in unprecedented detail. By studying the distribution of galaxies, galaxy clusters, and supernovae, the Dark Energy Survey aims to shed light on how dark energy has influenced the universe's expansion over billions of years. At the heart of this project is a powerful tool, the 570-megapixel dark energy camera, mounted on the Blanco telescope in Chile. This state-of-the-art instrument captures incredibly detailed images of the night sky, allowing researchers to observe millions of galaxies and measure their distances with remarkable precision. By analyzing these observations, scientists can trace the history of cosmic expansion and better understand the role dark energy plays in shaping the universe. One of the key findings from the Dark Energy Survey involves the large-scale structure of the universe. By mapping the distribution of galaxies and galaxy clusters, researchers have discovered patterns that align with predictions made by dark energy models. These patterns, known as Baryon acoustic oscillations, act as cosmic rulers, helping scientists measure how the universe has expanded over time. The data collected by the survey has provided strong evidence that dark energy is indeed driving the accelerated expansion of the cosmos. But the Dark Energy Survey isn't the only project tackling this cosmic mystery. Other initiatives like the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope are also designed to explore dark energy's effects on the universe. These missions will complement the findings of the Dark Energy Survey, offering new perspectives and refining our understanding of this enigmatic force. Together, these projects represent a global effort to answer one of the most profound questions in modern science. What is dark energy and how does it shape the fate of the universe? As we look to the future, the insights gained from these observational projects could revolutionize our understanding of the cosmos. By combining data from multiple sources, scientists hope to piece together a clearer picture of dark energy's properties and its impact on the universe's evolution. The Dark Energy Survey is just the beginning of this journey, but its contributions are already reshaping the way we think about the cosmos. With this in mind, let's explore another intriguing aspect of dark energy, its potential connection to black holes. Could these mysterious cosmic objects hold clues to the nature of dark energy? The answers might just bring us closer to solving one of the universe's greatest mysteries. Now, let's venture into one of the most fascinating and speculative areas of dark energy research: the potential connection between black holes and this mysterious force. Black holes, those enigmatic regions of spacetime where gravity is so intense that nothing, not even light, can escape, have long captivated scientists and the public alike. But could these cosmic giants also hold the key to understanding dark energy? Recent theories suggest that black holes might play a surprising role in the story of dark energy, and the implications are nothing short of mind-blowing. One intriguing idea is that black holes could be storing vacuum energy, a form of energy inherent to empty space itself. According to some physicists, the immense gravitational fields of black holes might interact with the quantum vacuum, the seething sea of particles and antiparticles that pop in and out of existence. This interaction could potentially link black holes to the effects we attribute to dark energy. If true, this would mean that black holes aren't just cosmic vacuum cleaners, but also reservoirs of the very energy driving the universe's accelerated expansion. But how does this work? Let's break it down. In the quantum world, empty space isn't truly empty. Instead, it's a dynamic, fluctuating environment filled with virtual particles. These particles briefly appear and disappear, creating what's known as vacuum energy. Some theories propose that black holes could absorb and store this energy, effectively acting as cosmic batteries. Over time, as black holes grow and merge, they might release this stored energy, contributing to the overall expansion of the universe. This idea challenges our traditional understanding of black holes and opens up new possibilities for explaining dark energy's influence. Another angle comes from the study of supermassive black holes at the centers of galaxies. These colossal objects, millions or even billions of times more massive than our Sun, are thought to play a crucial role in galaxy formation and evolution. Some researchers speculate that the energy released by these supermassive black holes could influence the large-scale structure of the universe, potentially aligning with the effects of dark energy. While this connection is still speculative, it highlights the complex interplay between gravity, black holes, and the universe's expansion. Of course, these ideas are still in their early stages, and much work remains to be done. The connection between black holes and dark energy is far from settled, and scientists are actively exploring these theories through observations and simulations. For instance, studying the growth rates of black holes over cosmic time could provide clues about their potential role in storing or releasing vacuum energy. Similarly, analyzing the behavior of black holes in different environments might reveal new insights into their relationship with dark energy. As we continue to probe the mysteries of black holes and dark energy, one thing is clear: these cosmic phenomena are deeply intertwined in ways we're only beginning to understand. Whether black holes are directly linked to dark energy or simply part of a larger cosmic puzzle, their study offers a unique window into the forces shaping our universe. And as we uncover more about these enigmatic objects, we may find ourselves closer to answering one of the most profound questions in science: what is dark energy, and how does it shape the fate of everything we see? With this in mind, let's shift our focus to another intriguing aspect of dark energy: the possibility that its strength might change over time. Could dark energy be evolving, and what would that mean for the future of the cosmos? The answers might just reshape our understanding of the universe itself. Now, let's explore a question that could fundamentally alter our understanding of the universe. What if dark energy isn't constant? What if its strength changes over time? This idea, known as the time variation of dark energy, challenges one of the core assumptions in cosmology, that dark energy has remained steady since the dawn of the universe. If dark energy's influence has evolved, it could have profound implications for the fate of the cosmos. To understand why this matters, let's revisit what dark energy does. It's the mysterious force driving the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. For decades, scientists have assumed that dark energy strength, often represented by the cosmological constant, has remained unchanged. But what if that's not the case? What if dark energy was stronger in the past, weaker now, or even fluctuating over cosmic time? This possibility opens up a whole new realm of questions about the universe's history and future. One compelling reason to consider this idea comes from observations of the early universe. By studying the cosmic microwave background and the distribution of galaxies, scientists have found subtle hints that dark energy's effects might not be as consistent as we once thought. For example, some models suggest that dark energy could have been more dominant during certain periods, influencing the rate of cosmic expansion in ways that differ from our current understanding. If true, this would mean that the universe's expansion hasn't been a smooth, steady process but rather a dynamic one, shaped by the evolving nature of dark energy. But how could dark energy's strength change over time? One possibility lies in the concept of quintessence, a dynamic field that varies across space and time. Unlike the cosmological constant, which remains fixed, quintessence could evolve, growing stronger or weaker as the universe ages. This would mean that dark energy isn't a static force but a dynamic one, interacting with the fabric of space-time in complex ways. If quintessence is real, it could explain why dark energy's effects seem to vary over cosmic history. Another intriguing angle is the connection between dark energy and the universe's overall energy density. As the universe expands, the density of matter and radiation decreases, but dark energy's density might behave differently. Some theories propose that dark energy's density could increase or decrease over time, altering its influence on cosmic expansion. This could lead to scenarios where the universe's fate isn't as straightforward as a big freeze or big rip, but instead depends on how dark energy evolves. The implications of a time-varying dark energy are staggering. If dark energy's strength has changed, it could mean that the universe's expansion rate has fluctuated over billions of years. This would challenge our current models of cosmology and force us to rethink how we interpret observations of distant galaxies and supernovae. It could also mean that the universe's ultimate fate is far more uncertain than we thought, with possibilities ranging from a gradual slowdown to a dramatic collapse or even a sudden acceleration. Of course, proving that dark energy varies over time is no easy task. It requires precise measurements of the universe's expansion rate across different epochs, as well as a deeper understanding of the underlying physics. Projects like the Dark Energy Survey and the upcoming Euclid mission aim to gather the data needed to test these ideas, offering hope that we might one day uncover the truth about dark energy's nature. As we ponder the possibility of a changing dark energy, one thing becomes clear: the universe is far more dynamic and mysterious than we ever imagined. Whether dark energy is constant or evolving, its study continues to push the boundaries of our knowledge, challenging us to rethink our place in the cosmos. And as we uncover more about this enigmatic force, we may find that the story of the universe is far from over. It's still being written. With this in mind, let's turn our attention to another piece of the cosmic puzzle: the role of neutrinos in the universe's expansion. Could these elusive particles hold the key to understanding dark energy's influence? The answers might just surprise us. Now, shifting our gaze to another fascinating piece of the cosmic puzzle, let's dive into the role of neutrinos in the universe's expansion. These ghostly particles, often called the ghosts of the cosmos, are among the most mysterious and abundant particles in the universe. But could they also hold clues about dark energy and its influence on the cosmos? The answer might just reshape our understanding of the universe's evolution. Neutrinos are incredibly lightweight particles that barely interact with matter, making them notoriously difficult to detect. Yet, despite their elusive nature, they play a significant role in the universe's dynamics. Billions of neutrinos pass through every square centimeter of space, and even through your body, every second without you ever noticing. But their impact on the cosmos is far from negligible. In fact, neutrinos could be subtly influencing the rate at which the universe expands. One way neutrinos might affect cosmic expansion is through their contribution to the universe's total energy density. While they are much lighter than other particles, their sheer numbers mean they collectively add to the energy budget of the cosmos. As the universe expands, the density of matter and radiation decreases, but neutrinos with their unique properties might behave differently. Some theories suggest that neutrinos could interact with dark energy in ways we don't yet fully understand, potentially altering the rate of expansion over time. Another intriguing possibility is that neutrinos could act as a bridge between dark energy and other cosmic forces. For instance, certain models propose that neutrinos might have a small but measurable mass, which could influence how dark energy interacts with the fabric of spacetime. If neutrinos do have mass, they could subtly affect the gravitational pull of large-scale structures like galaxy clusters, indirectly impacting the way dark energy drives cosmic expansion. This connection, though still speculative, opens up exciting avenues for research. The study of neutrinos also ties into one of the biggest mysteries in physics, the imbalance between matter and antimatter in the universe. Neutrinos are unique in that they can oscillate or change between different types as they travel through space. This phenomenon, known as neutrino oscillation, hints at new physics beyond our current understanding. If neutrinos are connected to dark energy, their oscillations could provide clues about how dark energy operates on a fundamental level. But how do we study something as elusive as neutrinos? Scientists use massive detectors buried deep underground or submerged in ice to catch the rare interactions of these particles. Experiments like the Ice Cube Neutrino Observatory and the Super Kamiok and detector have already revealed fascinating insights into neutrino behavior. As these experiments become more advanced, they could uncover new details about how neutrinos interact with dark energy and shape the universe's expansion. The implications of this research are profound. If neutrinos are indeed influencing dark energy, it could mean that the universe's expansion is shaped not just by a single mysterious force, but by a complex interplay of particles and fields. This would challenge our current models of cosmology and force us to rethink how we understand the cosmos. It could also mean that the fate of the universe is more intricately tied to the behavior of these ghostly particles than we ever imagined. As we continue to unravel the mysteries of neutrinos and their connection to dark energy, one thing is certain: the universe is far more interconnected than we once thought. Every particle, no matter how small or elusive, plays a part in the grand cosmic dance. And as we uncover more about these connections, we move closer to understanding the true nature of the universe. With this in mind, let's turn our attention to another intriguing concept, the holographic principle. Could this radical idea about the nature of reality shed light on dark energy and the universe's structure? The answers might just take us to the edge of our understanding. Now, let's venture into a concept that sounds like it belongs in the realm of science fiction, but is deeply rooted in theoretical physics, the holographic principle. This radical idea suggests that the entire universe might be encoded on a two-dimensional surface, much like a hologram. At first glance, it seems almost too bizarre to be true. But what if this principle could help us unravel the mysteries of dark energy and the structure of the cosmos? The holographic principle emerged from the study of black holes and the nature of information. Physicists discovered that the information about everything that falls into a black hole is somehow preserved on its surface or event horizon. This led to the idea that our three-dimensional reality might actually be a projection of information stored on a two-dimensional boundary. In other words, the universe could be like a cosmic hologram, with all the complexity we see around us encoded on a simpler, lower-dimensional surface. But how does this relate to dark energy? One possibility is that the holographic principle could provide a new framework for understanding the universe's expansion. If the universe is indeed a hologram, then the way space and time behave on large scales might be governed by the rules of this two-dimensional encoding. This could offer fresh insights into why dark energy exists and how it drives the acceleration of the universe's expansion. Another intriguing implication is that the holographic principle might help resolve some of the paradoxes in our current understanding of gravity and quantum mechanics. For instance, it could provide a way to reconcile the behavior of dark energy with the laws of quantum physics, which have so far proven difficult to unify with Einstein's theory of general relativity. If the universe operates like a hologram, then the interplay between dark energy and gravity might be far more intricate than we've imagined. The holographic principle also raises questions about the nature of space itself. If space is a projection of information, then what we perceive as empty space might actually be teeming with hidden structure. This could mean that dark energy isn't just a mysterious force filling the void, but something deeply connected to the fabric of spacetime itself. It's a mind-bending idea, but one that could revolutionize our understanding of the cosmos. Of course, the holographic principle is still a theoretical concept, and much work remains to be done to test its validity. However, if it holds true, it could provide a powerful tool for exploring the universe's deepest mysteries, including the nature of dark energy. It's a reminder that sometimes the most profound truths about the cosmos come from the most unexpected places. As we ponder the holographic principle and its implications, let's shift our focus to another fascinating aspect of the universe, the role of cosmic voids. These vast, empty regions of space might seem like mere gaps, but they could hold important clues about dark energy and the universe's structure. What secrets do these cosmic voids hide, and how might they shape our understanding of the cosmos? The answers could be closer than we think. Now, let's turn our attention to one of the most intriguing features of the cosmos, cosmic voids. These vast, seemingly empty regions of space stretch across billions of light years, forming a kind of cosmic web where galaxies and galaxy clusters are the threads, and the voids are the gaps in between. At first glance, these voids might appear as mere emptiness, but they hold profound secrets about the universe's structure and the influence of dark energy. Cosmic voids are not just empty space. They are regions where the density of matter is significantly lower than the cosmic average. Imagine the universe as a sponge, with galaxies clustered in the denser parts and voids representing the holes. These voids make up a staggering majority of the universe's volume, and their distribution tells us a lot about how dark energy shapes the cosmos. As the universe expands, these voids grow larger, and their behavior provides critical clues about the nature of dark energy. One of the key ways cosmic voids help us understand dark energy is through their effect on the universe's expansion. Dark energy, as we know, is the mysterious force driving the accelerated expansion of the universe. But how does this acceleration manifest in the vast emptiness of cosmic voids? It turns out that the growth of these voids is directly influenced by dark energy. As dark energy pushes the universe apart, it also affects the rate at which voids expand. By studying the size and distribution of these voids over time, scientists can measure the impact of dark energy and refine our understanding of its properties. Another fascinating aspect of cosmic voids is their role in the large-scale structure of the universe. The distribution of matter in the cosmos isn't random. It follows a pattern shaped by the interplay of gravity and dark energy. Cosmic voids are like the negative space in this cosmic tapestry, and their arrangement reveals how dark energy counteracts gravity on the largest scales. By mapping these voids, astronomers can create a detailed picture of the universe's structure and test theories about dark energy's influence. But cosmic voids aren't just passive observers in the universe's expansion. They also play an active role in shaping the behavior of galaxies and galaxy clusters. For instance, the gravitational pull of the matter surrounding a void can affect the motion of galaxies, creating subtle distortions that scientists can measure. These distortions, known as redshift space distortions, provide another way to study dark energy's effects. By analyzing how galaxies move in and around voids, researchers can gain insights into the strength and behavior of dark energy. One of the most exciting developments in this field is the use of cosmic voids as natural laboratories for testing cosmological models. Because voids are regions of low density, they are less affected by the complex interactions that occur in denser parts of the universe. This makes them ideal for studying the fundamental properties of dark energy and gravity. By comparing observations of cosmic voids with predictions from theoretical models, scientists can refine our understanding of how dark energy works and how it shapes the universe. As we explore the mysteries of cosmic voids, it's clear that these seemingly empty regions are anything but. They are windows into the workings of dark energy and the large-scale structure of the cosmos. By studying their growth, distribution, and influence, we can uncover new insights into one of the universe's greatest enigmas. And as we continue to map these voids with ever greater precision, we move closer to unraveling the secrets of dark energy and the fate of our universe. With this deeper understanding of cosmic voids, let's now shift our focus to the future of dark energy research. What groundbreaking missions and technologies are on the horizon, and how might they help us solve the mysteries of dark energy? The answers could redefine our understanding of the cosmos. As we peer into the future of dark energy research, a new era of discovery is on the horizon, powered by cutting-edge missions and technologies designed to shed light on this cosmic enigma. One of the most anticipated tools in this quest is the James Webb Space Telescope, often referred to as the successor to the Hubble Space Telescope. With its unprecedented sensitivity and ability to observe the universe in infrared light, the James Webb Space Telescope is poised to revolutionize our understanding of dark energy. By studying the earliest galaxies and the large-scale structure of the cosmos, this telescope will provide critical data on how dark energy has influenced the universe's expansion over billions of years. Another groundbreaking mission is the Euclid spacecraft, launched by the European Space Agency. Euclid is specifically designed to map the geometry of the dark universe, focusing on the distribution of galaxies and cosmic voids across vast distances. By measuring the shapes and positions of billions of galaxies, Euclid aims to create a three-dimensional map of the universe, revealing how dark energy has shaped its evolution. This mission will also explore the subtle distortions in light caused by dark matter, offering insights into the interplay between dark energy and dark matter. In addition to these missions, ground-based observatories like the Vera-C, Rubin Observatory are set to play a pivotal role. Equipped with the largest digital camera ever built, this observatory will conduct the legacy survey of space and time, capturing detailed images of the night sky over a decade. By tracking the motion of galaxies and the growth of cosmic structures, the survey will provide invaluable data on the effects of dark energy. The sheer volume of information gathered will allow scientists to test theories about dark energy with unprecedented precision. Beyond these observational efforts, advancements in theoretical modeling and computational power are also driving progress. Supercomputers are now capable of simulating the universe on a scale never before possible, allowing researchers to test how different models of dark energy influence the cosmos. These simulations, combined with real-world observations, are helping scientists refine their understanding of dark energy's properties and its role in the universe's fate. As we look ahead, the collaboration between space missions, ground-based observatories, and theoretical research promises to unlock new insights into dark energy. Each discovery brings us closer to answering fundamental questions about the universe's expansion and the forces that shape it. With these tools and technologies, the future of dark energy research is brighter than ever, offering the potential to solve one of the greatest mysteries in modern cosmology. Now, let's turn our attention to another fascinating frontier in the study of dark energy, the role of string theory. How might this complex framework of physics provide new perspectives on the nature of dark energy and the universe itself? The answers could reshape our understanding of reality. Now, shifting our focus to the realm of theoretical physics, let's explore how string theory might hold the key to unraveling the mysteries of dark energy. String theory, a framework that attempts to unify all fundamental forces of nature, proposes that the universe's building blocks are not point-like particles but tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to the particles and forces we observe. But how does this connect to dark energy? One intriguing idea within string theory is the concept of extra dimensions. Beyond the three spatial dimensions we experience, string theory suggests the existence of additional, hidden dimensions. These extra dimensions could play a role in explaining dark energy's effects on the universe's expansion. Some theories propose that dark energy might be a manifestation of energy stored in these higher dimensions, influencing the fabric of space-time in ways we are only beginning to understand. However, string theory faces significant challenges when it comes to providing testable predictions about dark energy. One major hurdle is the sheer complexity of the mathematics involved. String theory operates on scales far smaller than anything we can currently observe or measure, making it difficult to design experiments that could confirm or refute its predictions. Additionally, the theory allows for an enormous number of possible solutions, often referred to as the landscape of string theory. This vast array of possibilities makes it challenging to pinpoint which, if any, might correspond to our universe and its dark energy properties. Despite these challenges, string theory remains a promising avenue for exploring dark energy. Some researchers suggest that advancements in observational cosmology, such as more precise measurements of the cosmic microwave background or the large-scale structure of the universe, could provide indirect evidence supporting string theory's predictions. Others are exploring the potential connections between string theory and quantum gravity, hoping to uncover new insights into how dark energy interacts with the fundamental forces of nature. As we continue to probe the cosmos, the interplay between string theory and dark energy offers a tantalizing glimpse into the deeper workings of the universe. While the path to understanding is fraught with complexity, the pursuit of these ideas pushes the boundaries of human knowledge, challenging us to rethink our understanding of reality itself. Next, we'll delve into another compelling approach to explaining cosmic acceleration: modified gravity theories. Could these alternatives provide a simpler explanation for dark energy's effects, or do they introduce new mysteries of their own? The answers might just reshape our cosmic perspective. Now, let's turn our attention to a fascinating alternative to dark energy: modified gravity theories. These theories propose that what we perceive as dark energy might not be a mysterious force at all, but rather a sign that our understanding of gravity itself is incomplete. One of the most well-known examples is modified Newtonian dynamics, or MUND. This theory suggests that at very large scales, such as those of galaxies and galaxy clusters, gravity behaves differently than what Newton or Einstein predicted. Instead of requiring dark energy to explain the universe's accelerating expansion, MUND posits that gravity's strength changes under certain conditions, offering a potential explanation for cosmic acceleration without the need for dark energy. MUND has had some success in explaining the rotation curves of galaxies, which describe how stars and gas move around galactic centers. Observations show that stars at the edges of galaxies move faster than expected based on visible matter alone. While dark matter is the conventional explanation, MUND offers an alternative by tweaking the laws of gravity. However, when it comes to explaining the universe's large-scale structure and its accelerating expansion, MUND faces significant challenges. It struggles to account for the precise measurements of the cosmic microwave background and the distribution of galaxies across the cosmos, which are well explained by the standard model of cosmology that includes dark energy. Another approach within modified gravity theories is the idea of scalar tensor theories, which introduce an additional field that interacts with gravity. These theories suggest that this new field could mimic the effects of dark energy, causing the universe's expansion to accelerate. While intriguing, these models often require fine-tuning to match observations, raising questions about their simplicity and elegance compared to the dark energy hypothesis. Despite these hurdles, modified gravity theories remain an active area of research. They challenge us to rethink one of the most fundamental forces in nature and explore whether our current understanding of gravity might need revision. Some scientists argue that a deeper theory of gravity, perhaps one that unifies quantum mechanics and general relativity, could naturally explain cosmic acceleration without invoking dark energy. Others believe that while modified gravity might not replace dark energy entirely, it could offer complementary insights into the universe's behavior. As we continue to explore these ideas, the debate between dark energy and modified gravity highlights the dynamic nature of cosmology. Each approach offers unique perspectives, pushing us to refine our models and deepen our understanding of the cosmos. Next, we'll examine how cosmic inflation, the rapid expansion of the universe in its earliest moments, might be connected to dark energy and the universe's ongoing acceleration. Could these two phenomena share a common origin, or are they entirely separate mysteries? The answers could reshape our cosmic narrative. Now, shifting our gaze to the earliest moments of the universe, we encounter another profound mystery: cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching far faster than the speed of light. This rapid growth smoothed out the cosmos, creating the remarkably uniform universe we observe today. But here's where things get intriguing. Could cosmic inflation, this explosive beginning, hold clues about dark energy and the universe's current acceleration? At first glance, cosmic inflation and dark energy might seem like entirely separate phenomena. Inflation describes the universe's explosive growth in its infancy, while dark energy explains its accelerating expansion billions of years later. Yet, some scientists speculate that these two events could be connected. Both involve a form of energy-driving expansion, though on vastly different scales. During inflation, a hypothetical field called the inflaton field is thought to have powered the rapid growth. Similarly, dark energy is often described as a field permeating space, pushing galaxies apart. Could these fields share a common origin or underlying mechanism? One possibility is that the inflaton field, after driving inflation, transformed into the energy we now call dark energy. This idea suggests that the same force responsible for the universe's early expansion might still be at work today, albeit in a much weaker form. Another theory proposes that dark energy is a remnant of the quantum fluctuations generated during inflation. These tiny ripples in spacetime eventually grew into the large-scale structures we see, like galaxies and galaxy clusters, while also leaving behind a subtle energy that now drives cosmic acceleration. However, connecting inflation and dark energy isn't straightforward. The energy scales involved in inflation are unimaginably higher than those associated with dark energy. Bridging this gap requires new physics, potentially involving theories that unify quantum mechanics and gravity. Some researchers suggest that a deeper understanding of these fundamental forces could reveal a unified framework explaining both inflation and dark energy. Despite the challenges, exploring this connection could revolutionize our understanding of the cosmos. If inflation and dark energy are linked, it would mean that the universe's earliest moments are still shaping its destiny today. This idea not only ties together two of the most profound mysteries in cosmology, but also hints at a deeper, underlying order to the universe. As we ponder this possibility, we're reminded of how much remains unknown. The interplay between inflation and dark energy invites us to rethink the very fabric of space-time and the forces that govern it. Could these two phenomena be different manifestations of the same cosmic process? The answer might lie in the next generation of telescopes and experiments, which could uncover new clues about the universe's origins and its ultimate fate. Up next, we'll explore how dark matter, another cosmic enigma, interacts with dark energy, shaping the universe's evolution in ways we're only beginning to understand. Now, let's turn our attention to another cosmic heavyweight, dark matter. While dark energy drives the universe's accelerating expansion, dark matter plays a crucial role in shaping its structure. Together, these two mysterious forces form the backbone of our cosmos, influencing everything from the formation of galaxies to the fate of the universe itself. But how do they interact, and what does their interplay tell us about the universe's evolution? Dark matter, unlike dark energy, doesn't push the universe apart. Instead, it acts as a cosmic glue, holding galaxies and galaxy clusters together through its gravitational pull. Without dark matter, galaxies would fly apart, unable to maintain their intricate shapes and structures. Yet, despite its invisible nature, dark matter makes up about 27% of the universe's total energy and matter content, far outweighing the ordinary matter we can see. Dark energy, on the other hand, makes up roughly 68% of the universe and is responsible for its accelerating expansion. While dark matter pulls things together, dark energy pushes them apart, creating a delicate cosmic tug-of-war. This interplay between the two forces shapes the universe on the largest scales, determining how galaxies form, evolve, and distribute themselves across the cosmos. One of the most fascinating aspects of their relationship is how they influence the universe's growth over time. In the early universe, dark matter dominated, driving the formation of galaxies and large-scale structures. As the universe expanded, dark energy began to take over, gradually becoming the dominant force. Today, dark energy's repulsive effect is accelerating the universe's expansion, while dark matter continues to hold galaxies together even as they drift farther apart. But what happens when we look deeper into their connection? Some theories suggest that dark matter and dark energy might not be entirely separate entities. Could they be two sides of the same cosmic coin, linked by some underlying mechanism we've yet to discover? For instance, certain models propose that dark energy could arise from the properties of dark matter particles, or that both forces might be manifestations of a single, more fundamental phenomenon. Exploring this possibility could unlock new insights into the universe's evolution. If dark matter and dark energy are connected, it would mean that the forces shaping the cosmos today are deeply intertwined with those that governed its earliest moments. This idea challenges us to rethink our understanding of the universe's structure and the forces that drive it. As we continue to study these enigmatic components, we're reminded of how much we still have to learn. The relationship between dark matter and dark energy is one of the most profound mysteries in modern cosmology, offering a window into the universe's past, present, and future. Up next, we'll delve into how observational biases and limitations might affect our understanding of dark energy and the universe's expansion, shedding light on the challenges scientists face in unraveling these cosmic secrets. Now, let's shift our focus to a critical yet often overlooked aspect of cosmology, the role of observational bias. When we study the universe, the tools and methods we use to observe it can sometimes introduce limitations or distortions that affect our understanding of dark energy and cosmic expansion. These biases can arise from the way we collect data, the instruments we use, or even the assumptions we make when interpreting our observations. One of the most significant challenges in studying dark energy is the sheer scale of the universe. Our observations are limited to the light that reaches us, which means we're essentially looking back in time. The farther we peer into space, the older the light we're seeing, and the more our understanding relies on extrapolating data from the past to the present. This introduces a potential bias, as the universe's behavior billions of years ago might not perfectly reflect its current state. Another source of bias comes from the instruments themselves. Telescopes and detectors have limits to their sensitivity and resolution. For example, faint or distant objects might be missed entirely, or their properties could be misrepresented due to the limitations of our technology. This can lead to incomplete or skewed data, which in turn affects our models of dark energy and the universe's expansion. Even the way we analyze data can introduce bias. Scientists often rely on statistical methods to interpret observations, but these methods can sometimes amplify uncertainties or overlook subtle patterns. For instance, when measuring the universe's expansion rate, small errors in data collection or analysis can lead to significant discrepancies, such as the Hubble tension we discussed earlier. This tension highlights how even minor biases can have a major impact on our understanding of the cosmos. Additionally, the assumptions we make about the universe can shape our conclusions. For example, many cosmological models assume that dark energy behaves uniformly across space and time. But what if it doesn't? If dark energy's properties vary in ways we haven't yet detected, our current observations might be missing key pieces of the puzzle. This underscores the importance of questioning our assumptions and remaining open to alternative explanations. So, how do scientists address these biases? One approach is to use multiple, independent methods to study the same phenomenon. By cross-checking results from different observations, such as supernova, galaxy clustering, and the cosmic microwave background, researchers can identify and correct for potential biases. Another strategy is to continually refine our instruments and techniques, pushing the boundaries of what we can observe and measure. Ultimately, understanding and accounting for observational bias is essential for unraveling the mysteries of dark energy and the universe's expansion. It reminds us that science is an ongoing process of discovery, where each new observation brings us closer to the truth while also revealing new questions to explore. As we continue to refine our methods and challenge our assumptions, we move one step closer to unlocking the secrets of the cosmos. Next, we'll reflect on the philosophical implications of dark energy, exploring what it means for our understanding of existence and humanity's place in the universe. As we turn our gaze from the scientific to the profound, dark energy invites us to ponder questions that stretch beyond the boundaries of physics and into the realm of philosophy. What does the existence of dark energy tell us about the nature of reality itself? For centuries, humanity has sought to understand its place in the universe, and dark energy adds a new layer to this timeless inquiry. It challenges us to consider not just how the universe works, but why it exists in the way it does. One of the most striking philosophical implications of dark energy is its role in shaping the destiny of the cosmos. If dark energy continues to drive the universe's accelerating expansion, it could lead to a future where galaxies drift so far apart that the night sky becomes empty and dark. This raises profound questions about the meaning of existence in a universe that may one day become cold, isolated, and devoid of the vibrant structures we see today. Are we, as conscious beings, merely fleeting observers in a vast, indifferent cosmos, or is there a deeper purpose to our existence? Dark energy also forces us to confront the limits of human knowledge. Despite our technological advancements, we still don't fully understand what dark energy is or how it operates. This uncertainty reminds us that the universe is far more complex and mysterious than we can currently comprehend. It humbles us, highlighting the vastness of what we don't know and inspiring a sense of wonder about the unknown. In this way, dark energy becomes not just a scientific puzzle, but a philosophical invitation to embrace curiosity and humility. Moreover, the discovery of dark energy underscores the interconnectedness of all things. It reveals that the universe is not static but dynamic, shaped by forces that operate on scales far beyond human experience. This interconnectedness invites us to reflect on our relationship with the cosmos. Are we separate from the universe, or are we an integral part of its unfolding story? Dark energy suggests that we are deeply woven into the fabric of reality, connected to the very forces that drive the cosmos's evolution. Finally, dark energy challenges us to consider the nature of time and existence. If the universe is expanding at an accelerating rate, what does that mean for the future of life and consciousness? Could there be other universes, each with its own unique properties, or are we living in the only one? These questions push us to think beyond our immediate reality and imagine possibilities that stretch the limits of our imagination. In the end, dark energy is more than just a scientific mystery. It's a gateway to deeper philosophical reflection. It invites us to explore the nature of existence, our place in the cosmos, and the profound mysteries that lie beyond our current understanding. As we continue to unravel the secrets of dark energy, we are reminded that the universe is not just a place to study, but a story to ponder, a mystery to embrace, and a source of endless wonder. And with that, we conclude our journey through the 25 mysteries of the cosmic dark energy era, leaving you with this thought. What does the existence of dark energy mean for you, and how does it shape your understanding of the universe and your place within it? As we bring our exploration of the 25 mysteries of dark energy to a close, it's clear that this enigmatic force has reshaped our understanding of the universe in ways that are both profound and humbling. From the accelerating expansion of the cosmos to the intricate dance of galaxies, dark energy has revealed a universe that is far more dynamic and mysterious than we ever imagined. Each mystery we've uncovered, whether it's the nature of dark energy itself, the fate of the universe, or the philosophical questions it raises, has deepened our appreciation for the complexity and beauty of the cosmos. These mysteries remind us that science is not just about finding answers, but about asking better questions. Dark energy challenges us to think beyond the limits of our current knowledge, to explore the unknown, and to embrace the wonder of discovery. It invites us to consider our place in the universe not as passive observers, but as active participants in a story that is still unfolding. As we reflect on these 25 mysteries, let's remember that the journey of understanding is never truly complete. The universe is vast, and there is always more to learn, more to explore, and more to wonder about. So, as we conclude this journey, I leave you with this thought. What does the existence of dark energy mean for you? How does it shape your understanding of the universe and your place within it? If you've enjoyed this exploration of the cosmic dark energy era, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest videos. The universe is full of mysteries waiting to be uncovered, and we're just getting started. Until next time, keep looking up, stay curious, and never stop wondering about the incredible cosmos we call home.